architect Robert Woodstock, who's a Jamaican architect with over 45 years practicing in the Caribbean on many projects in many different islands. He has been the recipient of many awards. I would encourage you to read the bios again for those details.
As you are all structural engineers, most of you, you are the problem solvers. Today you've posed and given me a problem because I now start at the time that I should be finishing. So I beg you to bear with me. As architects, we are usually the problem creators for the structural engineer. But however, we are problem solvers for other factors. So today, I will attempt to explain to the engineers some of the problems, the reasons for the problems, and crave your understanding. Following on from Tony, I shall begin by repeating what Tony has said to me and emphasized many, many times. The most important architectural decisions that affect seismic performance are the critical decisions that create the building's configuration, its size and shape, and for structural purposes, the nature and location of resisting and non-structural elements within it. From a seismic performance standpoint, simple forms and shapes, as Tony has repeated and said again, are recommended over complex ones. The top drawing, a square or a rectangle with proportions like 1 to 1, 1 to 1.5, are considered simple and preferable to the lower plans that are elongated, L-shaped, or H-shaped. Similar to what Tony has said about the design of hurricane-resistant designs, Christopher Arnold states, a square plan provides a near-perfectly balanced system. He goes on to point out 9 configuration influences on seismic performance. The matrix to the right of these influences, redrawn from building configuration and seismic design by Christopher Arnold and Robert Reitherman, shows the 2 pairs of characteristics, horizontal and vertical, combined to define the 4 basic categories of building shapes. Simple plan, simple elevation. Simple plan, complex elevation. Complex plan, simple elevation. And complex plan, complex elevation. They contend that all building configurations can be related back to this matrix. Following on from Tony, I shall be repeating what he has emphasized to me several times. Since the ground motion is essentially random in direction, the resistance system must protect against shaking in all directions. In a building such as the building shown, and this is in Barbados, the resistant elements are most effective when placed on the 2 major axes of the building in a symmetrical arrangement that provides balanced resistance. A square plan provides a near perfectly balanced system. With all these constraints, symmetry, uniformity, regularity, and repetition, all the architects search for form and creativity, be stifled and restricted to a bland, seismically desirable building. In the past, most buildings were symmetrical, uniform, regular, and repetitive. 2 great classical buildings, the Parthenon in Greece and the Pantheon in Rome, can be used as examples. The Parthenon was built between 447 and 438 BC and is around 111 feet by 228 feet, roughly a 1:2 proportion. It stood firm for centuries in an area of moderate seismicity. It is symmetrical about both axes. it has a dense perimeter of 20%. Structural density, total area of all vertical structural elements, columns, walls, braces, etc., divided by the floor area. It has a small span, and a great deal of material is brought down to the ground. There are no internally generated lateral forces due to arching trusses. The interior space, however, is very small. The Pantheon has a span of 143 feet, which is the largest of antiquity, and for 17 centuries, it was an extremely simple configuration. A cylindrical dome with a large span dome and a rectangular portico added to it. Its structural density is also 20%. Walls resist thrust through shear mass. Extremely thick masonry walls can be more stable than one might believe. Vertical gravity force of mass is so great relative to lateral forces that the entire structure is kept firmly in compression at all times. So, if we know the ideal configurations to reduce vulnerability and ensure safe buildings, why do we have so many buildings that do not appear to follow these principles? At least part of the answer, one could argue, lies with the 5 points of a new architecture. As this conference looks back 30 years, I thought I would look back 100 years. What are these 5 points of a new architecture? 5 points of a new architecture, and the title replies to a set of principles a set of principles developed in the early 20th century by architect Le Corbusier. In his manifesto, they march the architecture modern architecture towards a new architecture in Paris in 1926. These principles emerged from his domino system that was developed as a response to the devastation in the World War I, whereby standardized components were used for a structural system with infill walls made up of war rubble and mass-produced fixtures and finishes with the aim to quickly solve the housing problem for the disadvantaged. The structural elements function solely to support the slabs and the stairs. The domino skeleton consisted of 6 thick concrete columns that simply carried 2 horizontal slabs, one as the floors and the other as the roof. The columns and slabs were connected by a staircase. Apart from this, nothing else was fixed, thus permitting a great flexibility. The name domino was the Latin for domus plus innovation, as well as the resemblance of the system of a pack of dominoes. The system was conceived as a solution to the post-World War I rebuilding problem. The domino system demonstrates Le Corbusier's awareness of housing not only as an important social and architectural problem, but also as an industrial process. Construction will be transformed into a scientifically run, large-scale activity where it could be reproduced very quickly. So what are the 5 points of architecture? The plan, raising the building on pilotis. The right-hand plan shows the old type of building fixed to the ground with continuous foundations. The left-hand plan indicates a new possibility by raising the building floor slab up on pilotis supported on individual footings. The old ground floor is freed for landscaping, vehicular circulation, services, and other things. As Le Corbusier stated, the rooms are thereby removed from the dampness of the soil. They have light and air. The building plot is left to the garden, which consequently passes under the house. This would be ideal, if not for earthquakes, for areas like our climate. Two, the open plan. The right-hand sketch shows a traditional load-bearing walled floor plan with small rooms, narrow openings, and thick walls. The left-hand sketch shows the new possibilities and flexibilities as the walls are separated or freed from the structural support system, the columns. The entire composition now appears light and airy. Le Corbusier describes point 2 as follows. The free designing of the ground floor plan. The support system carries the intermediate ceilings and rises up to the roof. The interior walls may be placed wherever required, each floor being entirely independent of the rest. There are no longer any supporting walls, but only membranes of any thickness required. The result of this is absolute freedom in designing the ground floor plan. That is to say, the free utilization of available means, which makes it easy to offset the rather high cost of reinforced concrete construction. Point 3, the roof garden. This green concept, a century before LEED and those other systems, was based on the philosophy that if one removed a garden or lawn to construct a building, then one should replace it with a similar green area on the building's roof. The right-hand sketch shows a traditional gabled roof, load-bearing wall section with basement. The left-hand drawing shows the new possibilities and flexibility now possible with a flat roof. The roof terrace satisfies a number of demands: rain-dampened layer of sand covered by concrete slabs. And the roof gardens display the highly luxuriant vegetation, shrubs, and even small trees up to 3 to 4 meters tall can be planted. In this way, Le Corbusier says, the roof garden will become the most favored place in the building. In general, roof gardens mean to a city the recovery of all the built-up areas. Point 4, the free elevation, the free design of the facade. This is similar to the open free plan, but in the vertical plane as opposed to the horizontal plane. The right-hand sketches show the old thick walls with small openings, while the left-hand drawing shows the possibility of having very long windows because it is now possible to extend the outer wall beyond the line of the structural columns. Le Corbusier says, by projecting the floor beyond the supporting pillars, like a balcony all around the building, the whole facade is extended beyond the supporting construction. It thereby loses its supportive quality, and the windows may be extended at any length without any direct relationship to the interior. Point 5, the horizontal window. The right-hand sketches represent the darkness of a room with 2 small windows. The top one, a perspective, while the bottom one shows the amount of and degree of light in 4 different zones of intensity. The left-hand sketch, on the other hand, with a long horizontal window, indicates how light an area room will now be by eliminating the 2 darkest zones. Together with the intermediate ceilings, the supports from the rectangular openings in the facade through which light and air enter copiously. The window extends from support to support and thus becomes a horizontal window. The overall concept for the new architecture, the new aesthetic, is realized and epitomized in the Villa Savoy, which was almost 100 years ago. Wikipedia describes the villa as follows. It was Le Corbusier's Villa Savoy that most succinctly summed up his 5 points of architecture that he elucidated in the journal L'Esprit Nouveau and his book Towards a New Architecture, which he had developed throughout the 20s. First, Le Corbusier lifted the bulk of the structure off the ground, supporting it by pilotis. These pilotis, in providing the structural support for the house, allowed him to elucidate his next 2 points: a free facade, meaning non-supporting walls that could be designed as the architect wished, and an open floor plan, meaning that the floor space was free to be configured into rooms without concern for supporting walls. The second floor of Villa Savoy includes long strips of ribbon windows that allow unencumbered views of the large surrounding yard, which constitute the 4th point of his system. The fifth point was a roof garden to compensate for the green area consumed by the building and replacing it on the roof. A ramp rising from the ground to the third floor terrace allows for an architectural promenade through the structure. This new movement created a new architectural aesthetic and was multifaceted, technical, economic, social, psychological, and political. It gave aesthetic validity to a very economical, unadored rectangular box for all building functions and emphasized thinness, the aesthetic of the delicacy and slenderness that steel and concrete structure had made. However, you have other buildings. For example, the Swiss Pavilion in France, also by Le Corbusier, and the famous or infamous Ministry of Education building by one of Jamaica's most influential architects, Wilson Chung, are landmark buildings and examples of the international style. However, they've also come under severe criticism as far as seismic performance is concerned. With respect to the international style in general, the Swiss Pavilion in particular, Christopher Arnold identifies irregular configurations as a 20th century problem and describes a number of characteristics not present in older masonry buildings that have led to poor seismic performance, as has been outlined by the previous speakers, including the 3 points of architecture. The building on stilts or pillar T, without fully understanding of the seismic implications of vertical structural discontinuity, designers often create soft or weak stories, as was elucidated by Tony earlier. The free plan and elimination of interior load-bearing walls, the replacement of masonry and tile partitions by frame and gypsum board greatly reduced the energy absorption capability of the building and increased its drift, leading to a greater non-structural damage and possible structural failure. And 3, the great increase in exterior glazing and the invention of the lightweight curtain wall, like freestanding planning, interior planning, the light exterior cladding greatly reduced the energy absorption capability of the building and increased its drift. Arnold concludes that it is clear that the attempt to encourage or enforce the use of regular configurations is frequently not going to succeed. The architect's search for original forms is very powerful. He recommends a strategy that exploits the benefits of the ideal configuration, but permits the architect to use irregular forms when they suit the design intentions. And these are some of those recommendations. The best seismic performance for the lowest cost is needed. The maximum predictability of seismic performance is desired. The most economical structural design and construction is needed, including design and analysis for code conformance, simplicity of seismic detailing, and repetition of structural component sizes and placement conditions. And he has noted a skilled seismic engineer who is sympathetic to the architect's design intentions should be used from the outset. And the architect, and this is most important to us, should be prepared to accept structural forms or assemblies that may modify the design character, and should be prepared to exploit these as part of the aesthetic language and the design rather than resisting them. The architect and engineer should both employ ingenuity and imagination of their respective disciplines to reduce the effect of irregularities or to achieve desired aesthetic qualities without compromising structural integrity. Extreme irregularities may require extreme engineering solutions, which may be costly. A soft or weak story, and that can't be overemphasized, should never be used. This does not mean that high stories or varied story heights cannot be used, but rather that appropriate structural measures be taken to ensure balanced resistance. So to close, I will use another Le Corbusier quotation that speaks to the important role of both the architect and the engineer. The engineer, inspired by the law of economy and governed by mathematical calculation, puts us in accord with the universal law. The architect, by his arrangement of forms, realizes an order which is a pure creation of his spirit. By forms and shapes, he affects our senses to an acute degree and provokes plastic emotions. By the relationships which he creates, he awakes profound echoes in us. He gives us the measure of an order which we feel to be in accordance with that of our world. He determines the various movements of our heart and of our understanding. It is then that we experience the sense of beauty. Thank you.